Good morning, chemistry students. Today we're looking a little bit more at atoms. So on the left here, we have spent quite a bit of time looking at molecules and atoms and how we define those as elements versus mixtures versus compounds when those atoms are connected together. What we're going to spend just a little bit more time on is looking at what exactly is that atom. So we've kind of seen these atoms, we've talked about them as particles, as being these little BBs, these little solid spheres of stuff. But what you might have recalled from ninth grade is that it turns out that atoms, like this carbon atom right here, are not exactly solid. So these atoms can actually be broken down into smaller things. And this picture on the right is showing us the protons and neutrons in the nucleus, shown by that arrow there pointing at the central nucleus there. And then around the outside are the negatively charged electrons. Now we'll talk more about the charges, the positives, negatives, all of that great stuff later on. For right now, we're just concerned about the fact that we can use this picture, this model, what's called the Bohr model, to gain a better understanding of what exactly are these atoms and why do they connect together to make compounds and to make molecules. So let's look a little bit at what's going on there. Okay, so again, this picture that we're using is what's called the Bohr model because it was developed by a Danish physicist by the name of Niels Bohr. So one of the most important pieces of the Bohr model is this central piece. Now, again, keep in mind that what we're picturing here is actually many times bigger, many times bigger than what we actually exists. So the nucleus here looks a lot bigger than it actually is compared to the atom. And we'll probably watch a video at some point, maybe even some Bill Nye, that shows us that at exactly relative size as to how small the nucleus actually is compared to the rest of the atom, because most of the atom is just some empty space. So in the nucleus, we have a couple of particles, protons and neutrons. And the way that we see these represented on the periodic table, and some of the patterns that we'll look at, are the atomic number, which is related to and is exactly the same as the number of protons. And then it's also related to the mass. So the mass is actually accounted for by both the protons and the neutrons. They make up the mass of the atom. Now, as we also said, around the outside we have the electrons, okay? And they are found in these layers that we call orbitals. Now, keep in mind, right, we use the term orbital, kind of like a planet orbiting, but it's not exactly the same. This is kind of a simplistic model of the atom and isn't exactly 100% accurate. But for what we're doing, it serves a function as to helping us understand some of the behavior of the atom, even if it's not exactly perfect. So the electrons are outside of the nucleus, around the outside of the atom, and they come in these different layers. Now, depending on which layer we're in, each layer can hold only a certain number of electrons. So we see kind of written out here, the first layer can hold 2 electrons, the second layer can hold 8 electrons, the third layer can hold 18 electrons. And as we go on out and add more and more and more layers, we've only shown 3 here, but there are more layers that we can add on top of that as we need to hold those electrons as you get more and more and bigger atoms. Now, one of the reasons why we focus mostly on the electrons is because the electrons are the most important piece of the atom as far as chemistry is concerned. The electrons are what create the chemistry. They explain why chemicals react in a certain way, why atoms connect together and bond in certain ways, and they're going to be kind of the big emphasis for understanding the structure of the atom at this point and relating it to the periodic table. And you'll see that in a later activity as well. So this is one of the things that we've seen when we did our periodic table activities, is we looked at how some of the elements have similar properties, and they react in the same ways, they combine in the same ways. So let's take a look at why that is. And I'll give you just a minute here to look at some of these atoms and draw those, right? So we're doing kind of a shortened Bohr model, so I'm not drawing the entire circular orbital, and I'm not necessarily drawing out each proton, but just showing here for hydrogen, there's 1 proton in the nucleus. This is the nucleus here. And then around the outside of the atom, there's 1 electron. Okay? And as we go down that first group, these are the alkali metals in group number 1 or 1A. We notice that lithium and sodium, which are the next 2 elements right below hydrogen, have some similarities. So Yes, they have a different number of protons and a different number of neutrons in the nucleus. They also have a few more electrons, so lithium has 3. Remember that first orbital we said can only hold 2 electrons. That second orbital, then we're going to put that third electron right there, okay, for a total of 3 electrons. Sodium, again, adding more protons and neutrons, a few more electrons, so again 2 in that first level. We said that second level can hold up to 8, so there's a full 8 in that second level, and then the third gets that last for a total of 11, right? So 2 plus 8 is 10, one more for that 11th one that goes on the very outside there. So what we should notice here is how on that outermost level of electrons for each of these atoms in that group is that they have exactly 1 electron in that outer level. Okay? And it turns out that it's not even all of the electrons that really matter, it's really those outermost electrons that are the most important, and those outermost electrons that make the chemistry. So let's look at one more group as another example. Okay, and that's the fluorine group, the halogens. And we'll do a similar idea, right? So again, showing the nucleus here, 9 protons, 10 neutrons for fluorine. Again, 2 electrons fitting into that first layer, that closest to the nucleus. And then we have 7 more that are going to go into that second layer. Chlorine, very similar. 2 electrons in the first layer, 8 in the second layer, and then that leaves 7 more on the outside for a total of 17 electrons. And again, continuing that pattern with bromine, 35 electrons, so we have 2 in the first level, 8 in the second level, 18 in the third level, and then that leaves us 7 more that go on the outside. So once again, just like group 1 over there, this is group 17. Notice that they all have 7 electrons in that outermost shell, and as we saw in the periodic table trends, we see that the outer electrons are related to why those elements react in the same way. So fluorine, chlorine, and bromine, the reason we call them the halogens is because they all have the same behavior. They all react in the same way, combine in the same way with other elements, and that's because of those outermost electrons. So in the next activity that you'll do, you'll look at those outer electrons and some of the patterns and how that relates to the periodic table.